Okay. Well, first, thank you for the invitation. This is really exciting. Um, so, I have been a ham since 1958 when I was 13 years old and was in the Boy Scouts, and our scoutmaster had this radio and he could talk to people. And I thought, that's cool. And Morse code, I could pick that up. So when I was very young, I got a license, but I didn't know anything. I just read the manual and memorized the answers to questions like you'd memorize the lines of a play. And I went through and up and up and up and upgraded. The Morse code was easy. But I realized I didn't really know or understand anything, but I could pass tests. So it wasn't until quite a few years later when I studied physics and astronomy and electronics. Oh, that's what that is. Oh, this is what a tube looks like. I even had to take the test where you would draw the circuit of an oscillator. And I knew you draw a circle, you put dots, and there's a squiggly line. I didn't know what any of them meant. But I could draw a one-tube Colpitts oscillator, and I didn't know anything. So it was kind of strange that over the next couple of decades, I learned a little bit here and there, became a physics teacher, and then I really had to learn to teach it to someone else. So it was kind of, funny that here I am 60 some years later after my novice license that I'm sharing what I think I have understood about this NanoVNA. Now, I have to be upfront. I didn't buy one. One of my favorite topics is antennas, feed lines, matching, tuners, and I gave a talk about a year ago to a local club, and the club members were buying these NanoVNAs, and someone asked me, "Oh, do you have one of these NanoVNAs?" And I said, "No, what's that?" So they bought me one, and they sent me a NanoVNA, and I said, "Wow, thank you. That's quite a prize here." And they said, "Well, we bought it for you, but we want you to learn how to use it and then teach us." I said, "Oh, that's fair." So about 3 months later, I gave my first NanoVNA talk, and I sort of said, I'm going to aim this at the third grade level. Very, very basics. So I've upped my ante, and I think I'm up to about a ninth grade understanding of this. I am not an RF engineer. I'm not going to open it up and show you all the beautiful circuitry in there. What I want to do, and I think it's more appropriate, is to show you this as a tool, one more tool in a ham radio operator's toolbox, how to use it. And that's my goal in, about 50 minutes here. We'll try. So let me go to screen share, and I'll work through what I've presented. Now, as a teacher, all right, did that come up?
Yes.
Yeah.
Yes.
Okay, all right. So as a teacher, I always kind of over prepare. So I thought, well, what would you folks like to learn about? And I've given this talk to about a dozen local U.S. ham clubs. And I found there's two kinds of people, two kinds of hams who would like to learn about this. One, someone who has no idea what a VNA is, but is kind of eager to learn something new. And the other is some of you who may have bought one and you're experimenting with it, trying it out, and want to learn more about it or how to fix it or whatever, but you've already played with it. So the first part, I just want to aim it at the basics of what it could be used for in your shack. And that will take about 45 minutes, I hope, if I talk faster. Part two is look under the hood. How does this really work? And then we get into a little bit more technical end of things. How does a reflection coefficient be measured? What is return loss? Hams don't use that. Why do antennas have reactance and impedance? Phase. What does phase mean on an antenna? A little more into the weeds. And the Smith chart. The first time I gave this talk, one of my friends said, don't mention a Smith chart. You'll lose everybody. So the Smith chart is in the end of part two. So if you really like part one, I'm available sometime later to do part two. All right, so we'll get started here. So right away I thought, well, this is just another tool. And I thought, oh, I remember when I was a teenager, I had one of these Swiss Army knives. And it also cost about $50 US money. When I was a teenager, I thought, this is so wonderful. And I got a present of a Swiss Army knife. I was 12 years old. So when I went camping with our scouts, I always took my Swiss Army knife. But I found I only used one or two of the tools there, the main blade, maybe the can opener. And it had all these other gadgets, but I never used them. But I always felt like I could. So this little NanoVNA is also about $50 American money. And, it's also a Swiss Army knife of sorts. It can do all kinds of things, but you may perhaps just want it to measure the SWR of your antenna or something. Now, a lot of us have used antenna analyzers in the past, sort of like these. I have a couple of MFJs, and they're very useful. They're also a couple $100. They're portable. They do what I need to do to check out antennas, but a NanoVNA is far, far more versatile and can show you much more about your antenna than any of these gadgets. Here's a really simple thing. You put an antenna feed line to measure SWR. Well, this is really simple. There's only a couple of parts. Coax in, coax out, tells you the power, tells you the SWR. Good enough for what that does. A fancier one. Couple of different scales, calibration, forward and reflective. Here's a very simple one. It's the most expensive, a bird watt meter. But these are limited what they can measure. For instance, if I know the SWR on my 80-meter dipole is 3 to 1, I don't know why. I don't know how to fix it. Just something wrong. With a NanoVNA, you can find exactly what's wrong and how to fix it. So it's much more functional. Then I thought of something else. This was almost in a dream when I woke up one day. I thought, well, a NanoVNA is sort of like a stethoscope. I like that analogy. A stethoscope, you put it on, you can listen to your heart. Our grandkids have much more fun listening to their gut, and they can hear all the rumbles and gurgles of their, intestines cranking along. But if you're sharp, you can sort of figure out something about your heart by listening to thump, 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 thump. A NanoVNA is sort of like an antenna stethoscope. You can detect some things about your antenna, but you have to know how to interpret that data or the graphs. Then I took it one step further. Now I'm just at the age, now I'm 76. I'm just at this age where I got to watch out my heart. So I get a EKG, electrocardiogram, every year, and the technician straps me up, 8, 10 leads. Psst, out comes an EKG on a piece of paper. And before the doctor comes in, I look at it and I'm thinking, I can interpret this. I know a little about EKGs. So my doc comes in and I say to the doc, how about if I take a crack at reading my own EKG? He knows me, retired physics professor. So he says, go ahead. So I describe, a couple of things and the amplitudes, and after a while I say, so how did I do? He said, not bad, about a third grader interpretation. I thought, that's a compliment. He said, Barry, you're looking at the amplitudes, which I was, nice peak here. You're looking at the amplitude, look at the phase. And I thought, oh, yes, the timing between the pulses and the recovery time also. So every year now when I go back to them, I get a little bit better at interpreting my EKG, and I know all about phase between this pulse and this pulse. This is just like it. The NanoVNA can measure phase. What's phase? Timing. So I'll show you why in a couple of slides ahead. All right, so if I just showed you this slide, this is a Smith chart. I was warned not to do this, but I'm going to do it anyway. Lead from the chin here. A Smith chart. I'm not going to tell you what it is, but here's a Smith chart. And this is my own 80-meter dipole antenna. And I have markers. I don't know if you can treat markers at 3.5, 3.6, 3.7, 8, 9, 4 megahertz. 4 markers. Here they are. 1, 2, 3, 4, 5, and 6. Now, without explaining anything about a Smith chart, can any of you look at that and say, yeah, I can see where your antenna is going to work best? So if you can, unmute and just call out an answer. Where will this antenna work best? Most likely. I'll say this. I calibrated it, so 50 ohms is the bullseye. That was a good hint. Mm-hmm. Where should this antenna work best? Which marker?
Perhaps number 3. I don't know.
Number 3. So number 3 is over here. So those of you that have some familiarity, 3 is a resonant point. There's no reactance at 3, but it's far from the bullseye. So on a typical Smith chart over here where marker 3 is, it might have a resistance of maybe 300 ohms. And with 50 ohm coax feed line, which is what I use, that wouldn't be a good match. 50 ohm to 300, 6 to 1 SWR. So 3 is resonant, but not a good match to my 50 ohm coax. I sort of gave it away when I said I calibrated my Smith chart where the center, the bullseye, center of the Smith chart is 50 ohms. So which of these markers is closest to the bullseye? Number 2, 3.6 megahertz. So 2 and 3 are both resonant, meaning there's no reactance. Some of you probably aren't sure what that means, but it means the impedance is a pure resistance. 2 happens to be very close to the bullseye, so 2, the resistance might be 45 ohms. Real good match to 50. 1, not very good, far from the bullseye. 4, 5, and 6, even worse. So we're going to come back, and by the end of the talk, I'm going to show you this again, and you're going to say, I hope, yeah, I get why a Smith chart is a good interpretation of at least this antenna. That's my goal. How about this one? See, my doctor said, Fearman, learn about phase, phase, phase. Well, I know what it means, but, you know, with an antenna, what does it mean? So here's my NanoVNA with the proper computer software showing me a phase plot. Phase. This is in degrees. Phase. This is frequency on the horizontal axis. Here's one weird graph of phase of my 80-meter antenna. What is going on? Negative 30 degrees, negative 190 degrees, and then suddenly, boom, up to 160 positive, and then something else. What's the phase telling me right in here? Can anyone unmute and just give me a quick third grader explanation?
The resonation point?
There's a what?
The resonation point.
Resonance point. Okay. So it's moving from a negative degree to a positive degree. So it's moving from a reactance that's negative to positive or capacitive to inductive. Something's magic happening here. Maybe that's the resonant point of the antenna. Ooh, that's kind of nice. Look what that's a pretty graph for a $50 instrument. Well, and a computer. How about this one? This is kind of confusing. The blue is resistance, ohms, and this color is reactance, also ohms. Same antenna. So if you look at this, could you say, oh, I see from this graph with my NanoVNA, where should this antenna work best? All right. Where? Well, here's resistance. 50 ohms or so is down here. So 50 ohms, that's pretty close to 0.2, isn't it? Also way out here, 50 ohms. But then the reactance, this graph, is some weird negative 50 ohms and so forth. Where's the reactance? 0. Well, 0 would be up around here, minus 2 degrees. So here's about where the reactance, this graph, is 0. Oh, it's also where the resistance is 50 ohms. Oh, that is a clue. So I can tell a lot about this same antenna by looking at resistance and reactance graphs, all with my NanoVNA. But I have to be smart enough to interpret what this graph means. That's a little tricky, isn't it? So what is this gadget? It's just another tool in the toolbox. Now, granted, it doesn't look like these tools, but it's just another tool. I loved it when I found this illustration. I thought, oh, I got to put this in. Great tool. Great tool. This one's a little more fragile. These you can beat up. All right, so I thought right away, well, what does the NanoVNA do? What does any VNA do? It sends out a signal and listens. What do you get back? Well, that's just like sonar, except sonar is now sound. So I lived and worked at a boarding school where we had a lake and we had bats. And the bats lived in the lake house up in the roof. And they would come out at night and hunt They were real good. They would go flying around after sunset, and they would emit these high-frequency chirps, chip, 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 chip. And it would be like echolocation for the bat, except it was like 80 kilohertz audio. Now, it's audio, not RF, right? Why 80 kilohertz? Because that's a teeny, teeny wavelength, and those small wavelengths could bounce off insects. And I guess the bat has two good ears, two good antennas here, and it could figure out where the insect was, and even if it closed its eyes, it could zoom in on an insect and eat it. So bats with good hearing, good echolocation, I guess, were fed better. They probably reproduced better, and so bats have real good hearing way up high. I don't. How about dolphins? Well, it's the same thing, except underwater, sound really travels wonderfully, and dolphins emit these, sounds, and they can echolocate other things like fish, food, other dolphins, all kinds of things. Submarines, well, it's the same thing. So the sub goes ping, ping, and sees what comes back and can locate things like maybe other subs. Okay, so the VNA doesn't mess with sound, but it does do kind of the same thing. So this is as technical as I'm going to get looking at the insides of this thing. So a flow chart of a vector network analyzer. Well, the word vector means it has directional capability. It also has phase or timing capability. A network and an analyzer. So it is what it says it is. It has a source, meaning a little transmitter. It sends out about a milliwatt, maybe less than a milliwatt of RF. The RF goes out on a cable, coax cable, and it goes to something that you want to test. I love this. A device under test, a DUT. I don't know how that translates to Portuguese. A DUT. If it's a filter, some energy goes through it, or an amplifier, some energy goes through it. If it's an antenna, there's no output. It's supposed to radiate. So on an antenna, we look for a reflected signal, measure that compared to the incident signal, and configure all kinds of things about the resistance, reactance, impedance of the antenna. So that's what I'm going to do with a couple of my antennas. And it has a way to separate the incident and the reflected wave, to measure the amplitudes and measure the timing, the phase. So when I hook it up to an antenna, my VNA goes through some sort of a cable, a feed line of some sort, goes to the antenna. If this is a perfect antenna, what should happen? Well, the antenna takes that RF signal and radiates it all. What comes back on the feed line? Nothing. I hope nothing. But what if there's a little mismatch and you get an SWR of 2 to 1, 3 to 1? You get a little reflected energy. Well, the VNA picks that up. It measures the amplitude, measures the phase, and compares the forward and the reflected voltages, and can figure out all kinds of stuff that we're going to look at. So it's just like, the dolphin going chirp, chirp, and waiting for an echo. What if the dolphin goes chirp, chirp, and there's nothing out there, no echoes? It's no food tonight, right? And where's my family? It's all alone. The most common question I have received is this like a spectrum analyzer? Yes and no. Now, a network analyzer sends out a signal and then measures the reflected wave or the through wave. A spectrum analyzer is just the receiver, a very good one. It can dice and slice the spectrum and do all kinds of things to it, but a spectrum analyzer is not a transmitter. It's just a receiver. But they both can look very sophisticated, intimidating. They both, in professional boxes, can cost, a lot of money. But there are differences and there are similarities here. I found a vector network analyzer by Roden Schwartz online, and I thought, look at this gorgeous thing. I wish I had one of these in my shack to play with. This cost as much as my automobile, a couple tens of thousands of dollars. But it has an input and an output, 2 ports, a lot of knobs and dials here, and fancy, and goes up to 6 gigahertz. But this is a professional vector network analyzer, certainly not a nano VNA. Then I came across this one. I thought, oh my gosh, look at this thing. Also a Roden Schwartz, very fancy company. A professional up to 20 gigahertz vector network analyzer. 4 ports, all kinds of ins and outs you can switch, and all kinds of displays and color. This costs more than my house. Now, I gave a talk to the Pentagon, U.S. Pentagon Amateur Radio Club. Yeah, the Pentagon Amateur Radio Club in Washington. And one of the listeners on the talk said, I use one of these. I said, you have one of these? He said, yes. I said, explain. He said, well, I work on the radar system of fighter jets at Andrews Air Force Base. And I use this device, this exact one, to align the radar systems on the F-35 Raptor jets or something or other. I said, wow, I'm impressed. So you know how to use this? He said, yes, it's part of my job. I said, do you get to take it home and test your antennas with this? He said, no. No, can't do that. He said, I also don't like to mix work and pleasure. But no, he doesn't take it home to analyze his antennas. But look at that. I would love to have that in my shack. So this is what I'm going to talk about, the NanoVNA, about 50 bucks. But I'll tell you, compared to these, it can do a lot, just 50 bucks. So what is it? Well, it sends out a signal on channel 0 and either can get a reflection back on channel 0, or you can send it through a device to channel 1, which is just the receiver. So it's a 2-port device. Look at it, beautiful in color, 4 colors, a touch screen. The red and the purple I don't see very well. So blues and purples, the yellows and the greens I don't see very well. I'm kind of colorblind. I knew that, but amazing device. Now here's one of its limitations for 50 bucks, and it's getting better every couple of months. It has a limited amount of memory inside to calibrate it. Calibrate it. What's that all about? I'll show you. And it has an internal battery that can last a couple hours in the field. So yeah, you could take it out on field day and align your antennas, and it's fine. It's a little difficult for me to read the screens with my eyes and bifocals and all. But if you've got younger eyes, shouldn't be a problem. Oh, it has these little, most of them have these SMA ports. That's hard to work with. So I purchased little adapter cables that go from SMA to the regular size, PL259 size cables. Another $10 for some cables. Now, here's what changed my life. I was playing with this thing for about a month, and someone said to me, have you hooked it up to your computer yet for computer control? I said, no, I didn't know you could do that. He said, well, of course. So I figured that out, went online, and I found NanoVNA Saver, Windows 10. That changed my life. Then it was really easy to calibrate it and use it. I had so much fun with it. So if you're going to use this, I suggest you use a computer software control to sort of like control the gadget. So now I don't even have to look at it when I control it. Little on-off power switch, USB connection. So this connect is charging the battery or the COM port for the computer. So NanoVNA Saver, I could talk about just about this for an hour, but I'm not going to do that. Very intuitive. Did I say it's free? Big thing, free. So once you load it and get it set up, you need to connect the NanoVNA Saver to your device through a COM port. This can be a serial port on your computer, or most of the computers now don't have serial ports, so a USB virtual COM port will work just as well. So when you hook it up, you have to connect it to a COM port, and right away mine said, oh, it's connected to COM 7, and that's called a NanoVNA. I didn't even type that in. So I click connect, and boop, done. In a few minutes I was in control of the device, and I felt much better. One of the nice things is to calibrate it. It's much easier to calibrate using the computer than using the device itself. You can pick many more ports. You can save the calibration files, and I'll show you an example of that. So calibration, what's that all about? Well, at the end of the NanoVNA, these SMA ports, they come in a way pretty stupid. You have to teach it what's a 0 ohm load, what's a infinite load, and what's a 50 ohm load if you want to calibrate it to 50 ohm. So it's called a SOL. So the O is open, meaning infinite resist, no connection between the center and the rim here. So even though this is a connector, there's nothing to connect the pin and the shield. So very, very high resistance. The short is exactly what it says, the S, a short. Just a wire connecting the pin and the shield. 0 ohms, no reactance. The L is the key. The L is the expensive one, the load. Now, most of us who use 50 ohm cable want to calibrate this VNA on 50 ohms. So inside here is a high precision 50 ohm resistor, non-inductive, and that's the expensive part. So when I set my NanoVN up over some frequency range, I have to plug these screw these in into the SMA connectors on the VNA. So what I do is say, all right, so I want to standardize, let's say from 3.5 to 4 megahertz, okay? And when I sweep, I have to look at what's happening between 3 and 4 megahertz when I put on these different standards. So after I've done that, I have a file, and that file might have, anywhere from 100 to thousands of data points. I save that file on my computer, not on the VNA. So I can call that and I do 80 meter calibration or 40 meter calibration or 20 meter. Now, someone said, why don't you just calibrate it from 1 to 500 megahertz? I could do that, but I see no reason to do that. I'd rather have calibrations for each of the bands that I'm interested in. And if I calibrate it over a wide frequency range, I'm going to need a lot more data points. But that works. You can select markers, colors, all sorts of things. I don't want to spend too much time on the software. Built in, the one I have can store only 101 data points. Well, that's fine for 80 meters, 40 meters, 20 meters. It's not so good when you say, I want to do the 70 centimeter band, 420 to 450 30 megahertz with only 100 data points. That's not so good. So I don't save the calibrations on the device itself. I use the computer. You can calibrate it with a short, open, and load, and also the through to go with 2 ports and an isolation. So most of my calibration files are about 5,000 data points. So it's, maybe a 100K file, and it takes maybe less than 1 minute to do my calibration. Then I save it. It can display all kinds. Yes.
Can I just make a query? Can you go back one extra slide?
Yes, here.
If I understood correctly, then by default you have 101 data points, but then you can multiply it here under
yes, right there.
control,
yeah.
right?
Yep.
That is
right
just
there.
like the density. So if you put 2, you have
Yes.
202, and so on.
Yes.
Okay.
So if I put 50, it's 50 times 100, 5,000, and that's what I usually do. But you don't need that many data points for, let's say, 40 meters or 20 meters.
Yeah.
Yes.
Okay, sorry, Barry.
Yeah.
Eu não sei se queres aproveitar e fazer alguma tradução para quem possa, da tua dúvida que colocaste ao Barry, ok?
Yeah, so I'll just I'll just switch very quickly to Portuguese, Barry.
Yeah.
Aqui a ideia, os NanoVNAs normalmente têm, pelo menos estes de entrada, têm só 100 pontos, ou 101 pontos. Quer dizer que ele basicamente vai partir do início ao fim da frequência, neste caso 3.5 a 4, vai dividir isto em 101 pontos e depois esses são os pontos que nós medimos. Neste caso aqui vai dar 5 capas. Nós temos este multiplicador, é um tal I1, podemos pôr aquilo 2 ou 3 ou 4 e basicamente ele vai encurtar esta densidade para termos muito mais pontos. E isto só se consegue fazer com o NanoVNA Server no computador. Se alguém tiver alguma pergunta, precisar de tradução, estejam à vontade. Okay, sorry, Barry. It was just faster. Just basically translating what
I would say if you don't do the calibration correctly, it's garbage in, garbage out. This is useless as a tool.
Of course.
So I just pulled up one of my displays on one of my antennas. Look at this. It's just gorgeous. I could set the color anything I want, and I can see these colors very easily. Blue is good. And so this is just 80 meters looking at a Smith chart. Looking at what's called S11, that's a reflection coefficient. I haven't defined that. Looking at phase, that's odd. Looking at resistance and reactance, return loss, that's an engineering term. SWR, well, we're familiar. All of this, and this took about less than 1 minute to make all these graphs with the computer. I look at this and I say, oh, I understand everything about this antenna. Now remember, I'm doing this from my shack about 150 feet from the actual antenna. But I can infer from these graphs what it would be like if I put the NanoVNA right at the antenna. That is, if I'm clever, I can calibrate it 100 feet away. So why would I want one of these? I love this slide. It's like, so? Well, it's one cool gadget. So I'm going to check out some of my own filters. I'm going to check out some coax. I'm going to check out some antennas. I don't want to get too deeply into the calibration or the Smith chart. If you want, we can do that another time, and I'd love to talk about that, but that's not the thrust of today's talk. So I have some cable, some coax cable, and I want to measure, is it okay? What's the length? Can I still use it? So I hook up coax cable to this port, or maybe through one of the adapters, and this little device can do what's called a TDR, time domain reflectometry, TDR. What does that mean? It's the equivalent of the NanoVNA sends a pulse down the cable. At the end of the cable, I just short the pin in the shield. What happens when the signal gets there? Well, it's 0 ohms. It just reflects right back. So the signal goes down the cable, comes back, and this NanoVNA catches the return signal. From that, and knowing basically how fast a radio wave moves in any of these cables, it can tell me the length of the cable and if there's a break anywhere. I thought, oh, that's cool. Let me try it. So I took a bunch of cable. I had a whole roll of this. It was about it's about 100 feet or so. And I set it up for time domain reflectometry. And I pinged it, you can see up here, from a tenth of a megahertz to 30 megahertz. I stopped there. And it sends a signal down, and look, it gets a big reflection at about 28 meters down the coax. And then nothing. Well, 28 meters, that tells me, and this is a one-way transmission, not both. So the coax is about 28 meters long. But more important, how about before? There's no break in the coax. So my connectors are okay, my shield is okay. I don't think I have any water in the coax, but I'm not sure. But it looks like, hey, this is pretty good coax, RG8X. Belden, pretty well named. So, all right, could I use this on 80, 40, 20, 10 meters, 2 meters? So I now want to test what's the attenuation. What's the coax absorbing or attenuating? So now I set it up a little differently, and I look at the return loss of the signal. The signal goes out, hits the end of the cable, comes back, but not all the signal comes back. Why not? Well, because every cable has attenuation. So at 1 megahertz, the attenuation is about 1 decibel right here. 1 dB, well, that's about 10%. I'm not going to worry about 1 dB unless I'm doing moon bounce. How about at 6 megahertz? Oh, now the attenuation is 2 dB. I can live with a 2 dB loss. That's not much. How about at 20 meters? Oh, now I've got about a 3 dB loss. Now I'm getting a little concerned. 3 dB, that's half the voltage. That's a quarter of the power. Well, how about over here, down here at, remember this is plotting frequency down here, not length, frequency. How about at 6 meters? Oh, no, wait a minute, 6 meters, marker 5 here, 51 megahertz. Now the loss is 6 dB. The SWR is about 3 to 1. Oh, I know, that's not very good, right? Maybe I shouldn't use this cable on 6 meters. Buy a better cable. So, and it's got a little zigzag, which is kind of interesting too. So I can measure the attenuation at different frequencies. No, I just stopped at 100 megahertz. Thought, well, that was kind of fun to do. I'd never done that before with a $50 NanoVNA. So, how about measuring inductance capacitance? I used to teach physics. I thought, well, there's a lot of ways to measure inductance and capacitance. So this little gadget can measure all kinds of things, including resistance and capacitance. How does it do it? Well, it's got a clever circuit involved, so I just found this and I thought that's kind of fun. I recognize a lot of the formulas here. So how does it do this? All right, so we're going to have to backtrack 1 minute and take a look at coils and capacitors. What are they? How do they behave? And how can my NanoVNA check these out? I'm looking at the time, so I don't want to spend too much time here. Well, inductor or a coil? Well, it's just a wire wrapped in a circle here in a coil. Well, why does this have what we call inductance? Well, it's interesting. When a current goes through a coil, it makes a magnetic field, Faraday effect. So if I just plug it into a battery, it's just a magnetic field, a little electromagnet. But what if I put an AC signal through this? Oh, that becomes a little trickier. The current goes one way, the current goes the other way, the current goes the other way. Every time the current switches direction, this inductor fights it. It resists it. It acts as a resistance. So what it behaves as though is a switching magnetic field that has to collapse, rebuild, collapse. and it features a property called inductive reactance, a fancy word for AC resistance. As the faster I try to switch the current, the more this thing resists. It's sort of like your finger. I used to say to the kids, do this. Well, that's pretty easy. I can move my finger fast. Now move your whole wrist as fast as you can. Well, that's not too bad. I can do that. Now move from your elbow. Oh, that's harder. Now move your whole arm. Oh, that hurts. So inductance, it acts as though it's a kind of inertia in mechanics. So the current decreases as the frequency goes up through an inductor. So its resistance is a function of frequency. That's what we call inductive reactance. There's a formula for it. I'm not going to drive that. 2 pi, just a constant FL. So the L is the inductance. What does that mean? Well, it's related to the number of coils, the spacing, and other junk. How about a capacitor? Well, my students used to call them capacitators. I don't know why. Capacitors behave just the opposite. A capacitor is 2 conductors separated by an insulator. And here's a whole bunch of them here. So when an electron comes to one plate of a capacitor, it creates an electric field and pushes a different electron off the other plate. So I said to my students once, explain that back to me so that I understand it. So they built a model. They brought in a big cardboard box that came like from a refrigerator, and it had 2 holes cut into it. And one of the kids got into the box, and he had a couple of tennis balls. So one of the students took a yellow tennis ball and threw it into one of the holes in the box. So the yellow tennis ball went into the box. Then the kid in the box took a blue tennis ball and threw it out of the other hole. So a yellow tennis ball came in, a blue tennis ball goes out. So 1 electron in, 1 electron out. Guess what? The capacitor is still neutral. But it's got a positive charge on one plate. It's missing its electron. And a negative charge on the other plate. So charging a capacitor charges one plate positive, one plate negative, and I gave those kids an A. That was a great illustration. The yellow tennis ball never went through. A yellow tennis ball went in, and a blue tennis ball came out, emphasizing it's not the same electron. 9th grade mind. Okay, so what about capacitors? If you switch really fast, the signal gets through. But if you switch too slowly, the capacitor sort of fills with charge, sort of like the dam, fills with electrons, and then it pushes back any additional electron. So low frequencies can't get through a capacitor. The capacitor blocks low frequency. It passes high frequencies. So the resistance of a capacitor, called capacitive reactance, the formula for that is 1 divided by 2 pi FC. The important thing here is the F's in the denominator. As F gets bigger, right, the X sub C gets smaller, a bigger number in the denominator. My 9th graders weren't sure about that. All right, so capacitors and inductors behave differently on AC. See where I'm going? So what happens where a capacitor and an inductor are connected to a circuit and their reactances connect at the same point, have the same value? The interesting thing is they behave in different ways, and they can cancel their own effects. So a capacitor and an inductor in a circuit can form a resonant circuit. Well, that's a big word, resonance. So let's take a look at that. So you can hook up capacitors and coils, either in series or in parallel, and they behave completely different ways. Let's take a look here in parallel. Some frequency. The current's coming through here. It has a choice. It can go through the coil or the capacitor, right? It's a two-way street here. So low frequencies can easily pass through the coil, but not the capacitor. High frequencies, really high frequencies, can pass through the capacitor, but not the inductor. So if it's a really high or low frequency, this thing is a pretty low resistance. So here we go. The capacitor itself can pass the high current. The inductor can pass the low frequency. And it's the middle frequencies that are going to get blocked here. How about the series circuit? Well, it's just the opposite. Now the current has to get through both of them. First through the capacitor and then through the inductor. So low frequencies are going to get blocked here. High frequencies get blocked here. So it's only the mid-range kind of frequencies that can sneak through both. So as a resonant circuit, these have completely different characteristics. So the series I just kind of mentioned. What can get through is a resonant frequency and the highest current. The amplitude is maximum. I want to show that with my NanoVNA. If it's a parallel tuned circuit, like this, the low frequencies, no resistance. The high frequencies, no resistance. But the resonant frequency can't get through either. So a real high impedance, high resistance at resonance. Low current. I can show that with my NanoVNA. I'm sorry it's taking so long to get here. So, I'm going to show you some examples. When I was a youngster, I had one of these filters, a Drake low-pass filter. It was famous because back in the 1960s and 70s, we had analog television, and a lot of ham radio operators like me, a 13-year-old. I was getting into my neighbor's televisions. That's not a good way to make friends, right? So I bought one of these, a Drake low-pass filter. That was expensive, but I put it on my Heathkit transmitter when I was on 15 meters, and look what's inside this. It's all passive devices. Coils and capacitors, coils and capacitors. Drake low-pass filter. I thought, well, this saved my hide because I stopped getting into a lot of my neighbors' televisions once I put this device between my transmitter and my antenna. Antenna was a 40-meter dipole, and as a novice, I operated on 40 and 15 meters. All right, I'm talking kind of fast because I'm looking at the clock. So can I test this with my NanoVNA? So I take my NanoVNA out of channel 0, some coax going into here, and the output goes around here into channel 1. So I'm now looking at the through signal. The transmitter is sending a little milliwatt of signal through here at different frequencies, and I measure what comes out. What does come out? Oh, look what comes out. This is on my NanoVNA. So here's frequency from 1 megahertz to 100 megahertz. Here's the S21. That means the through signal. The gain. Well, the gain's 0. Well, it's not an amplifier, but there's no loss either. So in other words, it lets these signals, 10, 20, 30 megahertz, go through unattenuated. That's good. So I can operate with this filter on 80, 40, 20, 10 meters, the ham bands. But not on 6 and 2 meters. Back then I couldn't anyway. So at 4, that's about 35 megahertz. Look what happens. Whoa. None of the high frequency stuff can get through here. The gain is minus 80 dB. Minus, meaning that's a loss, right? 80 decibels, that's, let me think here, that's 100 million. So there's nothing getting out of this filter that's going to bother a television, right? Or not much. So suddenly I had more neighborly neighbors. How about this? I pulled this out of my junk box. Here's a coil and a capacitor, and it's mounted in some plastic here. What's this gadget? Looks like a coil and a capacitor, and as I look at it, they're mounted in parallel. So here's what it looks like on the side view. A connector, and I thought, oh, this is a parallel LC circuit. It's often nicknamed as a trap. I don't know how that translates in Portuguese. So I connect my NanoVNA to it the same way. Signal comes in. It's got to get through here. Signal goes out back to my NanoVNA. What should this look like? Oh, so here are my connectors. Kind of crude. Hey, I'm on a low HF frequency. I'm not like at 1 gigahertz, so my sloppy coax here. But so I thought, well, let's see what my NanoVNA makes of this thing. So it looks like this. The channel 1 goes through this gadget, and what comes out goes to channel 2. So I'm looking for resonance. What would I look for? Here it is. Whoa, look at this graph. The S21 is the gain, the through signal. Here's the gain of 0, meaning what? Well, at 3 megahertz, 4 megahertz, 10 megahertz, it's blocking a little bit, but look what is happening here. At about 14 megahertz, it's blocking about 65 dB. That's a loss. In other words, a 14 megahertz signal can't get through this. Can't get through the capacitor, can't get through the coil. It's being blocked. It's a high impedance just at this frequency. Oh, now we see why it's called a trap. It traps those frequencies, and it's like, the plant that grabs the food that way. So how do these frequencies get through? Well, they're low frequencies. They can go through the coil. How do these frequencies get through at 20, 30, 50 megahertz? They can go through the capacitor. So the trap is kind of a narrow frequency trap. Perfect. So I can use this as a 20-meter trap on a dipole. How about this? I have one of these in my shack right now. So it's called a duplexer. Actually, it should be called a diplexer. Here's the common. So I attach, let's say, my transmitter to here, and I have a 2-meter antenna and a 440 antenna. This gadget separates the 2-meter over here, 1.3 to 170 megahertz, VHF port, and over here a UHF port. What's inside here? How does it do that? So I looked it up, and here's a rough, quick schematic. So the radio connects here, and there's two choices. It can go through the coils. Remember, coils block high frequencies, but let lower frequencies through. And here, the capacitors. Capacitors send the high frequencies through and block the lower, and then of course they're capacitors to ground and inductors to ground. So this port allows the 2-meter energy to get through. This port allows the 70 centimeter, 440 megahertz energy to get through. And I hope these little elements here will allow one radio to work on 2 antennas, not at the same time, but I mean separate. So here's what I did. I hooked it up to my NanoVNA. So sure enough, when I connected to the 170 megahertz port, 2-meter port, 2 meters gets through easily. Here's 2 meters way up here. The reduction is 0. There's no reduction. But the reduction is, whoa, look at this. The reduction is 50 dB at about 280 megahertz, and then stays pretty low here. Kind of an interesting bounce here. So here's my 440 port. What's the reduction? About 30-some decibels. Oh, now I see how it works, and I could measure the isolation between the 2 ports. Here's the UHF port. So 440 port. None of the 2-meter stuff gets through. Look at this. The 2-meter stuff gets blocked by about 80 dB, and nothing gets through that. But then here, up at around, 300 megahertz and above, all that gets through. So beautiful. My little $50 NanoVNA just showed me how this thing works. And in fact, this thing cost as much as my NanoVNA. All right, so what else? Let's test out some antennas. I'm looking at the clock, and I've got 10 minutes, then I got to stop here. So let's play with some real antennas. Yes?
Barry, sorry to interrupt. I don't know about the rest of the audience, but we can stretch a bit the agenda. So it's
okay. See, it's only 5 o'clock for me, so I can go 2 more hours.
Most of us, for most of us, it's after dinner, and
yes, I know. Yeah.
And it's Friday, so we can
okay.
We can stretch it a bit.
Well, I'll show you some of the important slides testing antennas. So, what can I measure with this little $50 device? Resistance, reactance, impedance. Well, they're all keywords, and ohms. Phase. Well, I haven't really defined what that is with an antenna, but that's the key. This gadget can measure phase. My SWR meters can't. Reflection coefficient. Oh, I never heard of that. Return loss. If you're an engineer, you know what that means. SWR. Oh, I think I know what that is. And a Smith chart. Oh. All right, so let's take a look. So I have a multi-band dipole fed with coax. Now, in my case, I just have one trap here and here. And the trap is called a 40-meter trap. And I want to test it. I put it up about 2-3 years ago. It works fine. But now that I have a NanoVNA, I want to test it out. So, can my NanoVNA show me how well my trap antenna is working? Yes. So here's what the traps are. They look like this. I didn't make them. I bought them. They're made by a company called Unidillo, I think. Anyway, there's a aluminum cylinder here and here. Notice they're 2 different sizes. This aluminum tubing does not touch this one. There's an insulator between them. Ah, that's the capacitor. And then there's a coil of wire. More turns, more inductance. This particular one is set for 40 meters, 7 megahertz. So it's a parallel LC circuit. It's a trap. So it looks like this. So at the resonant frequency, about 7 megahertz, 7 megahertz can't get through the coil or the capacitor. It's kind of an open, high resistance. So it can't get through, so it's showing me the return loss is pretty big here. Oh, that's what I expected. How about the whole antenna? Well, here's what my whole antenna shows. 40 meters, low, this is SWR. SWR is about maybe 1.3, 1.4. That's pretty good on 40 meters. So it looks like my antenna is cut for the low end of 40 meters. Hint, I operate CW. How about the other parts? No, this is awful here. How about 80 meters? Oh, pretty good. Right in the middle of the band, about 3,800 kilohertz. The SWR looks like it drops to almost 1-to-1. Perfect. So how does that happen? Well, attached after this, I have about another 20 feet of wire, which then resonates on 80 meters. How does the 80 meter signal get through this? It sneaks through the loading coil. In fact, I call it a loading coil. The 80 meter can sneak through here, 3.5 megahertz, but not through here. So this acts to shorten the last part of the antenna. So that's what a loading coil does. It takes a longer wire and compresses it into a inductor coil. All right, I've got this antenna in my backyard. This isn't a picture of my antenna, but it's the same antenna. It's called a Cushcraft R5, multi-band vertical. Very nice. Up here, I wish I could expand this. There are traps. Traps for 10, 12, 15, 17 meters. Here's a blow-up of a trap. So a Cushcraft trap looks like this. Metal conductor, insulator. There's a coil of wire. So this is my inductor. The capacitor is fascinating. Here's a conductor, a conductor, a conductor. Oh, wait a minute. This wire and this wire, they don't touch. So it's looking like a piece of coax, a capacitor. So this is the capacitor side, this is the inductor side. And if you get the values just right, this can resonate at 10 meters, 12 meters, so forth. So these traps isolate the different parts of the antenna. So my one antenna, fed with one piece of coax, can operate on multiple bands, a trap vertical it's called. Here's the SWR graph from 12 meters, 20 meters. 20 meters looks pretty good. The SWR is about 1.2 to 1. All kinds of junk here. 18 megahertz, not so good, about 2.5 to 1, not impossible. I could adjust it a little bit, couldn't I? But I didn't bother. How about 15 meters? It's not so good. It's about 2. But look, I could have adjusted it. So this tells me not only my SWR, but if I want to improve it, I know I need to take this antenna down and adjust the coil or the capacitor so this resonant frequency moves up a little bit. And you can tell it's easier to mess with the coil than mess with the capacitor on these. Here's 10 meters. So beautiful. This is convincing me this is a good $50 investment. I could fix my Cushcraft R5 antenna to have a lower SWR on some of these bands. I just didn't bother. I'm lazy. All right. Well, I operate on 2 meters 440. There are these multi-band antennas. This is a gorgeous little J-pole. It's not mine, but I have one. And a typical dome type of 2-band antenna. So here it is on SWR, looking at 2 meters, very low, resonant around 146 megahertz. The SWR across the band's about 2 to 1. I can work with that. Here it is on 440. The SWR is less than 1.5 to 1 across the whole band. That's really nice. It also has these funny little bounces. That's part 2. But the SWR is pretty low here. Here's another antenna in my backyard. You can tell my backyard has a lot of antennas. A 2-meter beam. Now this is interesting because how you match it. Coax in, and it's got this funny gadget. This is unique to Cushcraft, called a gamma match. This is a capacitor right here. This wire and this don't touch. It's coax and metal here. And then where it connects. So by moving this back and forth, I can change the inductance and capacitance and move the matching point. Why do I need to do that? Because a multi-element beam has an impedance of maybe 20, 30 ohms. And I'm feeding it with 50 ohm coax. That's no good. So this is my matching right at the antenna itself. All right, so I tried it from my shack, and here's what I get. So here's the impedance. Goes all the way up to 100 ohms and down to about 30 ohms. That's quite a bounce there, isn't it? And look at this. The SWR goes up to 2 to 1 and then drops. But I operate mostly down in the low end of the band. It works fine. But I'm looking at this and think, oh, look at this. I can get the impedance a little bit more flat here and the SWR down here by doing what? I need to move this tap. And if you're clever, you can figure out which way. But it means taking the antenna down, fiddling with it, putting it back up. But here, my NanoVNA can tell me how to fix this antenna. All right, I'm going to end with this. My 80-meter antenna. This is my favorite antenna. It's an inverted V, but it's a dipole. It's about 135 feet long. It's fed with good quality, 150 feet because it's way out in my yard. WTU balun. I use this on 80 meters, and I'm thinking, hey, maybe I could use this on other bands. Let's test with my NanoVNA. So I ping it from 3 megahertz to 30 megahertz and measure SWR. Look at this. Well, 80 meters. The SWR is like 1 to 1. Well, it should be. It's an 80-meter antenna. And then look at 40 meters. The SWR is almost 7 to 1. That's no good. Well, I knew that wasn't going to be very good. But look, I could use it here at about 11 megahertz. Oh, no, I don't have a license to operate there. But that's resonant and low SWR. That's the third harmonic. Up and down, up and down. Not very good here on the other ham bands. Oh, look at this. SWR is almost 1 to 1 at 19.2 megahertz. Oh, bummer. My license doesn't let me transmit there. That's the fifth harmonic. So you see where I'm going here. I can use this NanoVNA to look at all the harmonics of this antenna, but the only one where the harmonic is both resonant and close to 50 ohms is right about here on 80 meters. The other resonant spots are outside the ham band. I can't operate there. So let me end by showing you this. Here's all 6 graphs of this antenna. Now, I said I don't want to go into gory detail and define reflection coefficient and Smith charts and all, but I can take this data, graph it, and in 1 or 2 minutes looking at this, I know everything about this antenna. I know where it works well. I know where it should work well. I know where it's not going to work well. Look at the Smith chart. The bullseye is what I want because I calibrated this on 50 ohms. Position 2, that's about 3.89, 3.589, 3.6 megahertz. Well, that's where I like to operate. Hint. How about the SWR? The lowest is, at about 3.6 megahertz. That's where I like to operate. But look at the top end of the band. The SWR is 3.5 to 1. Oh, that's awful. My radio won't work well up there. The phone part of the band. This is called a reflection coefficient. This is called a return loss. I'll talk about that if you invite me back for another hour. Resistance and reactance. That's doing something weird, but look at this. I want to concentrate here. Phase. Remember, I showed you that graph a little while ago. What's this antenna doing at 3.6 megahertz? Oh, it's changing the phase from capacitive to inductive. What does that mean? It means, what the analogy I like to do is picture a kid on a swing and you're pushing the swing. Your grandchild's on a swing and you're the grampy pushing. How do you know when to push? Well, every kid knows that. You want to push to get the kid swinging higher and higher. But how do you know when to push? Well, you push when what? Your push is in phase with the kid's natural swing. Even grandkids know that. They don't use those words. But what does that mean? It means the phase has to be just right. The timing. Think of timing. If I push too soon on the swing, I'm going to crash into my grandkid and get banged up. That's no good. If I push too late, I'm running after my grandkid. That doesn't work well. So this phase graph is telling me where Grampy should push. Grampy should push at 3.6 megahertz. Oh. Now I've got a lot more slides, but I need to stop because I said I'd stop at 1 hour. And let me just see what's next. Oh, this was the first slide I showed you. So here's a Smith chart of this antenna. Where's this going to work best? At position 2, 3.6 megahertz. How do I know that? Because it's close to the bullseye. What's the bullseye? What's special about that? I calibrated my VNA with a 50 ohm, no reactance load. So the bullseye represents 50 ohms. Out farther from the bullseye is either higher or lower resistance or reactance, either way. So reactance is up here, down here. Low resistance is over here. High resistance is here. And I have another whole hour talk to explain that, but not tonight. So let me hit stop share. I'm on a roll here. There we go. I hope that was kind of a whirlwind 3rd or 6th grade explanation of the NanoVNA in my Philadelphia English. There we go.
Okay, very well. Thank you. Well, let's say open this for Q&A. So not sure if any of our colleagues have any questions to Barry.
And you know what I did? I have a live VNA going right now. Here, let me just share screen with the other one. Did that pop up?
Yeah.
Here's a live reading of this 80 meter antenna. And I'm just showing you return loss, which is sort of like SWR, but a slightly different measurement.
Mm-hmm.
Look at this. It's tuned to about 3580 kilohertz. Now, right now, I have the signal going through an antenna tuner in my shack. In my shack, not up at the antenna. So I'm going to turn one of these dials and then hit sweep and watch what happens. I don't even know what's going to happen. Let's see. I'm going to mess with one of these dials. And I'm going to go sweep. This should only take a few seconds. Oh, done. That was fast. But look, I moved the lowest SWR up to 3700. Oh, just by turning a dial in my shack. Let me turn it back the other way and see what happens. Sweep. Now I'm messing with an antenna tuner in my shack. Oh, now look what I did. Not so good. Now the resonant point is slightly out of the band. So I'd like to, if I'm invited back sometime in the future, show you how an antenna tuner can cancel reactance from inside my shack. I don't have to climb up a tower and mess with the antenna up there. I can do all the messing down here in the warmth and comfort, or the cool today, of my shack. So what I'm showing you here on the display is just return loss. Let me change that to SWR, which you guys are probably more comfortable with. VSWR. So here's the SWR, and I'll move it back. Something like this. So here's looking at the SWR. There we go. What if I look at the display setup? Whoops. Display setup, and look at the favorite by far is the Smith chart. That tells you everything if you can interpret it. There we go. So if I tune one dial and hit sweep, I'm going to get a new antenna. Look at that. What have I got? See, the whole thing has moved and rotated around. So in other words, this is kind of tricky and not easy to understand. What I'm changing is the impedance of the feed line in my shack, after 150 feet of coax. Am I changing the SWR up at the antenna? No, no. Now I'm changing the SWR in my shack so my radio is happy and my radio sees 1-to-1. But all I'm doing is modifying the reactance in my shack to cancel the reactance that's already up at the antenna. That's what an antenna tuner does. So let me hit stop share, and I'll... Whoops.
Yep.
Okay.
Back to you, Barry.
So I'm ready for questions.
Well, this for me was way beyond the NanoVNAs. Actually, some of the constructs on the antennas, some of those more physics concepts of.
I'm a physics professor.
There you go. So, for me personally, I think it was outstanding. I learned a ton. So thank you. And I believe there's no way we were gonna pass the offering for that second.
I didn't mean tonight. I mean in a few months.
No, I got it.
Invite me back.
I'm pretty sure we will invite you back. So to demystify some of these constructs, the SWR, the return loss and phase, and all of that. I think we'll go then down.
I've tried to avoid that stuff because that's easy to get lost on that.
Yeah, but
reflection coefficient, return loss, SWR. What is reactance anyway? Why do antennas have that? That's all interesting stuff, but that's not 3rd or 6th grade. That's about 9th or 10th grade level.
I think we got all the constructs that we can measure with the NanoVNA. That's really good. So now I'm gonna digest some of this, and then we go deeper on this. Yeah, there you go.
There's my physical one. Now, I didn't buy this. People always say, where should I buy one? I don't know. I was given this as a present, and the folks who bought it on Amazon. And as long as you trust the distributor, there's a lot of varieties of these. Some of them have N connectors now. Some of them have bigger screens. Some of them have more memory. Mm-hmm. Some of them cost a little more, like $100. But
yeah, no,
it's certainly a lot less expensive than the big MFJ and Rig Expert antenna analyzers.
Yeah, I'm pretty sure, and I think we don't need to do this kind of precisions like tuning the radar of fighter jets. So I think we can leave it
I was impressed. I found this beautiful picture, and I thought, that's impressive. And the guy says, I use one of those at work.
Okay, so I'll have one question from my side. And when you were talking about the traps, where you normally aim the traps is to the lower part of the band, right? I'm assuming. So if I want to split between 20 and 40s, I'll go a bit below the 20s, so that I can enjoy the full band without harming the any lost on that, right?
There's a lot of debate about that, but I think of a trap as one and only one frequency in the trap. But some antenna manufacturers of the beams have one big aluminum tube, and when you open it, like Mosley and Cushcraft, when you open it, there are two traps inside. One's 20 meters, or one's 10 meters, one's 15 meters in one aluminum tube, but they're really two separate traps side by side, separated by about 4 inches of wire. Each trap is good at one and only one frequency, but you can build multiple traps within one container, sort of.
Okay, good. So opening the Q&A, the questions and answers for the rest of the colleagues.
One difficult question, CT1DOF. When there will be a second part? I'd like to
I can email you a PDF of, I've got like 150 slides. I can email you the whole thing and you can read it, but I can't talk that fast, especially.
Yeah, so definitely we will book, of course, depending on Barry's availability, and go down. I think people are more eager to go down now this SWR route and phase and all of these cool cool topics.
Can I talk?
Yeah. Hi, Ricardo, please go ahead.
I'm sorry, Barry. Thank you very much to be with us, and it's a very nice. I have here also analyzer, and my analyzer can read the impedance, of course, but to make the chart is another thing, and I think this gadget now permits us to see all the characteristics of the antenna. But I have to ask you, we have to make the calibration all the time. When we want to measure, we have to make the calibration with the
SMAs terminators, right? The small SMAs.
I'll bring up it live and I'll show you. You just do it once.
So you're using the NanoVNA directly, Ricardo, or are you using through the VNA saver?
I'm not using. I don't have a VNA. I have a. One of those.
Okay, one of those. Okay, got it.
Oh, that's different though.
Yes, but
that's one port. Yeah, that's not an in and out. All of the antenna analyzers like Rig Expert, MFJ, they're generally calibrated internally, so you don't need to calibrate those. This, you absolutely need to calibrate it.
Every time. I'm
no,
sorry.
No, not every time.
Now I put the microphone on my mouth. I'm sorry.
Here, let me share
Not
this.
every time. Only once when
Yes.
we hook up.
Did I make this large?
Yeah, we're seeing it very. Yeah.
Okay, so if I go to calibrate, calibration down here. I couldn't find it. I go to calibration, and I have a calibration assistant. I love it. I have an assistant. So I say, I'm going to say reset, meaning I'm going to wipe out any calibration. I just did. I hope I can get it back. Now I want to load the calibration. Now, I save the calibration on my computer, not in the NanoVNA. So I go to NanoVNA files, and here are my calibrations that I've already done. Once I've done them and saved them, every time I want to use this device, at least here in my shack with this computer, I just say, all right, which of the calibrations I want to use? So, and you can see the size. So this is a big file, 600 kilobytes, 1 to 500 megahertz. That's a huge range, 2 ports. I did that once just for play. How about 1 to 30 megahertz, where I usually work, 2 ports, 260 kilobyte file. So I click on this, and I load that file back into the NanoVNA. So I've loaded it, and now it says, now it has that file. So now I can set up to, and this is still connected. I'm going to take the antenna tuner offline and sweep again. Bingo. What antenna am I on? I don't even know. So here's one of my antennas. I think it's the same antenna. So here's my, here are the results. Yeah, that's the same antenna, I can tell you. But it looks like I moved some dials or something. So the calibrations I can save either in the NanoVNA itself, but they can only save 100 data points at a time. But that's fine. I could make an 80 meter calibration, 40, 20 meter, 10 meter. I wouldn't want to make anything larger range because I only have 101 data points in this particular one. I think as newer NanoVNA devices come out, they'll have 200 points, 500 points. It's just, you know, it's like the old computer. My first computer had 48K memory, an Apple II. I thought, why do you ever need more than 48K memory? You know, it's like 48K, wow. So, but once you save a calibration, then you've got it. Now, there's something else you can do, and I didn't show you this, but since you asked. What if I want to calibrate it, but not on the edge of my device, the NanoVNA? What if I attach, let's say, 100 feet of coax that I have here in my room, 100 feet of RG8 coax. And at the end of that 100 feet, now I put the calibration standards there. What have I done? I've eliminated the coax. So now my NanoVNA, the calibration plane, is 100 feet down the line. 100 feet's kind of nice because that's what? A half wavelength on 80 meters in the coax. Coax is what, about 130 feet, you know, for 80 meters, but the velocity factor is about 0.8, so 8 times 120, about 96 feet. Hey, 100 feet, roughly. So every time I buy 100 feet of coax, I'm thinking, oh, I've got a half wavelength at 80 meters. Why is a half wavelength good? Oh, that's a special number, right? So if I measure, if my antenna is 1/2 wavelength away, and I measure in my shack, it's identical, the readings, almost identical, than if I took the NanoVNA right up to the antenna itself. Half a wavelength, or 1 wavelength, or 1.5, you know, integer multiples of a half wavelength, the impedance duplicates. So that's the 10th grade understanding of this stuff. But this allows you to do the calibration plane anywhere. So I can just say, all right, I'm going to make a calibration with 100 feet of coax, another calibration with 200 feet of coax, within reason.
But I think it's fair to to assume that if we want, every time we switch the frequency range from start to stop, say I wanted to go from 430 to 440, and
yes.
every time we have a different frequency envelope, we need to calibrate. And then we can.
Oh yes, but I would do that ahead of time and save all those frequencies on my computer. So I did that. I mean, I did that like 3 months ago. Yeah.
So, yeah, I think that is the way to go, Ricardo. So if you wanted to adjust it for 2 meters or 7 centimeters, then you calibrate it immediately before the test, or you calibrate it beforehand and then you save it and
just
you
save it.
Cover those calibration
When
files.
you first turn on the NanoVNA, if you just turn it on and you're on battery power, it defaults to, I think it's called calibration 0. I call it 1, but you know, engineers call it 0. So that's the default when you first turn it on. But then I can go with a little mouse into the NanoVNA, reading it, you know, little print, and I can pick calibration file 1 or 3 or 5, but you can only at 5. On the one I have, you can only save 5.
Okay, and the measurement made in the feed point, at the feed point, is better or more accurate than down there and with the feed line present?
Only if I'm really at high frequencies like 2 meter 440, 1 gigahertz, where my feed line has a lot of attenuation. On 80 meters, 100 feet, the attenuation's a half a decibel. I don't care about a half a decibel, you know. So I think what you said is true, but I don't worry about it on HF frequencies.
Okay, thank you. And the use of adapters change the behavior of the measurements?
Yes. At very high frequencies, like 1 gigahertz, absolutely. In fact, these connectors, most folks say, don't use this kind of connector above 2 meters. Don't even use it on 440. It's not 50 ohms anymore. So I haven't played with this thing up above 440. And most of my antennas, I don't want to mess with them anyway on 440. But I wouldn't go from SMA to this. You can go from SMA to an N connector, or you can just buy the VNA hardware that already has N connectors on it. I think those cost about $100.
I know that at least we can try to so we calibrate it directly at SMA ports, and then if we put these kind of pigtails or direct adapters, then of course we will uncalibrate it. But I think there's some sort of hack on the NanoVNA where we can basically add some jitter or some extra points to try to push it back to what would be the 50 ohm bullseye, right?
I think that's true. Someone said they use a lot of 75 ohm coax for some reason. So they calibrated their Smith chart and their VNA with a 75 ohm load. Mm-hmm. You have to buy that. When this arrived at my doorstep, remember, I didn't buy it. It had the 3 standards in the box: the short, the open, and the load. The load was 50 ohms. But online, you can get a 75 ohm load, a 600 ohm load. And when you go up to the higher frequencies, like 1, 2, 3, 20 gigahertz, then the standards cost, $100, $200, $500. So this guy that works on, fighter radar systems, I should have asked him, what kind of standards do you use to calibrate? Because if his VNA cost $250,000, it's probably no big deal to use the standards. It's $1,000.
Indeed. Ok, any further questions?
Aproveitem então para fazer as questões que têm a fazer.
Ivo, desculpa, isso é para ti. O que é isto do bullseye?
Bullseye.
Ok, bullseye, portanto, o Smith chart ou seja, it's I can go in English. So the Smith chart it's like a circle, right? And if you put it on a line, you have like the open. So on this line here, so the horizontal line that is exactly at the middle, it represents a 50 ohms load. So if you basically put a 50 ohm resistor at the top of your SMA, assuming that it's calibrated, you'll have a point at center of this chart that it's like a bullseye, like the arrow stuff that we use.
I can show you the 3 standards on my Smith chart. I just thought that was too deep into the woods, so I love this. Like, what?
It's me.
Smith. Okay, so yeah, I understand that. So here's where my 0 standard plots on the Smith chart. This is on the NanoVNA I have right in front of me. 0 ohms plots there. So this is called the resistance axis on a Smith chart. This is where the open plots at the other far end. Now, 0, infinity, I mean many thousands of ohms. But it's not a linear scale. So the next is the key. What do I want to make the center? I want to make the center 50 ohms. Why 50? What's magic about that? Well, the antenna says 50 ohms. My radio says 50 ohms. The coax says 50 ohms. So I can't change that. So when I put on the 50 ohm standard, here's where it plots. The prime center, it's often called. So I've defined on my Smith chart, once I calibrate it, 50 is the bullseye.
Yeah, so as further we go away from the center, the worse will your antenna resonate.
Yes. So on terms of resistance, 50 is the center, but it's a geometric scale. So 10, 25, 50, 100, 200, 500, infinity over here. So the resistance is all these circles. All these are, so everywhere here along the circle, there's 5 ohms of resistance. But 5 ohms resistance, no reactance is just this point. As you move up, you get into what's called inductive reactance. As you move down, you get into capacitive reactance. That's Grampy's pushing too soon or too late. So if I look at a couple of values, here's 10 plus J25. Now this is into the weeds. 10 ohms resistance, 25 ohms positive reactance. So this arc is 25 inductive, and down here 10 ohms. So 10 plus 25, 5 plus J50 would be like an 80-meter hamstick. It's not going to work very well. In fact, I measured it. That's about what it is. So the farther you get from the bullseye, up here, that's not good. Down here, that's equally not good. It just means Grampy's pushing too soon or too late. Either way, that's not good. What if you're over here, no reactance, but 10 ohms? Well, that's good if I had 10 ohm coax, but I don't. I have 50 ohm coax. So here's one of my favorite slides. You want to be in the bullseye, 50 ohms. Why? Because I have 50 ohm radio outputs and 50 ohm coax, and my antennas are usually about 50 ohms. I'll stop with this one. So if you have a 50 ohm, no reactance antenna, and you plot it with a NanoVNA, it plots at one point right there, at one frequency. What if I ping it across the whole band and it always stays there? Then I know there's something wrong. No antenna will do that. Well, maybe a 50 ohm dummy load. Now I'm not even sure that would do it. But so the ideal spot when you use a Smith chart, the ideal spot if you're using 50 ohm coax is the bullseye if you calibrate it to 50 ohms. The farther away you get in any direction, the SWR goes up, the reflection goes up, you're in trouble. Grampy's in trouble. He's not pushing right. And I've given away part of my next talk, so I'm going to stop.